Hello and welcome to this video on the inverse Laplace transform. Last time we said that whenever you have an ODE, an ordinary differential equation, then you can apply the Laplace transform and you can go to the S domain, and there you have an algebraic equation. You get rid of the derivatives. Then you can apply the inverse Laplace transform, we'll talk about this today, and you can have your solution in terms of time, as a function of time, rather than as a function of s. In the time domain, you have, let's say you have a function little f of t. You apply the Laplace transform, and then you have the function f, big F of s. The inverse Laplace transform of big F is exactly this function little f. Of course, there is a tacit assumption that the Laplace transform is a one-to-one function, so it is invertible. This is not 100% mathematically rigorous. We'd have to state Lerch's theorem, but I want to skip this and keep this video short. So let's just think of the Laplace transform as a one-to-one correspondence between functions in the time domain and in the S domain. Examples: we already know that the Laplace transform of 1 is 1 over s. This means that the inverse Laplace transform of 1 over s is 1. Likewise, where does 1 over s plus a come from? It comes from e to the minus at. The inverse Laplace transform of omega over s squared plus omega squared is sine, and this formula here gives cosine. In general, we'll be working with functions in the S domain that look like this. They look like polynomial over polynomial times perhaps this exponential function. This is called a delay, but we can ignore it for now. We'll come back to this later. These functions that are polynomial divided by polynomial are known as rational functions. And here we'll be working with rational functions where the denominator q has a degree which is strictly larger than the degree of the numerator. And such functions are called strictly proper. Now we identify three different cases when it comes to determining the inverse Laplace transform. Case number one is where the polynomial q in the denominator has, let's say, n many distinct, different from one another, real roots. And these roots are called actually the poles of this function. So this is one case. The second case is where q has a factor of the form s minus something, s minus a real number, to the power n. We say then we have a multiple real pole. And the last case is where you have factors of this form, s minus a squared plus b squared, a and b are real numbers, and this implies that the complex number a plus minus b j is a pair of poles of the function. So we'll examine these cases separately. So once again, here we have the distinct roots a1, a2 up to an. Q has these distinct roots, which are real numbers. In this case, Q has a multiple root, can be a double root, a triple root, and so on. And here we have pairs of complex conjugate poles. So let's look into case number one, distinct real poles. And here is an example. Let's say we have the function 2s plus 3 divided by s plus 1, s plus 2. Let's do a quick sanity check. It is polynomial over polynomial. The numerator has degree 1. The denominator has degree 2, which is greater than 1. So we're good to go. So what we'll do here, because it's not evident what the inverse Laplace transform of this is, we will decompose it into what is called partial fractions. So we take this s plus 1 and we make a fraction with s plus 1 and with some unknown constant in the numerator plus some number b over s plus 2. So the claim is that we can take this fraction and write it, decompose it like this. We can write it like this. Something over s plus 1, something else over s plus 2. So to determine a and b, what we'll do is that we'll multiply by the denominator to get rid of the fractions, so to speak. So I've written this out here so we can see clearly what is happening. So I'm multiplying by s plus 1, s plus 2, all the terms of the equation. Here everything cancels out. Here just s plus 1 cancels out, and here s plus 2 cancels out. Great. So after we do this, we end up with this equation, and we can rearrange things a little bit and collect the s's on the right hand side. So we have clearly written a polynomial of s. So we have something times s plus a constant. So now what we have is that we have on the left hand side, we have a first order, first degree polynomial, and on the right hand side we have a degree 1 polynomial as well. And this is an equality of polynomials. So polynomials being equal means that the corresponding coefficients are equal. The coefficients of s must be equal, so a plus b must be equal to 2, and the constant coefficients must be equal, so 2a plus b must be equal to 3. We write these equations here, and we see that we have a linear system of 2 equations and 2 unknowns. So we can solve it. Hopefully it's solvable, it is, and we get a equals 1, b equals 1. Now that we know a and b, we have, you see, a is 1, b is 1, means that I can go here and substitute 1. I can write it like this. I can write my function as 1 over s plus 1 plus 1 over s plus 2. And now it's evident what the inverse Laplace transform is. The inverse Laplace transform of this is e to the minus t. The inverse Laplace transform of this is e to the minus 2t. Let's do one more. Say you have this expression where you have a polynomial divided by a polynomial. You have a rational function, you have a degree 1 numerator, a degree 2 denominator, you have a strictly proper rational function. Okay, we're good to go. But here, the denominator is not written in such a clear way as it was written before. If I scroll up, you see before we had s plus 1, s plus 2, it was factorized, and we could clearly tell that the poles are indeed minus 1 and minus 2, they're both real, and we did what we did. Now it's not clear, so we need to determine the poles. We take the discriminant, delta, we find it to be equal to 1. Then we need to determine the poles of the denominator. These are minus 1 and minus 1/2. And this allows us now to factorize the denominator. The denominator is 2s squared plus 3s plus 1. So to factorize it, 2s squared plus 3s plus 1, you see this 2, we keep it out as a constant, and then we do s minus the first root, s minus the second root, and this is your factorization. Don't forget this number 2. So 2s plus 1, s plus 1/2. And we have now factorized the denominator, and now it becomes clear what we need to do. We need to write this as a over s plus 1 plus b over s plus 1/2. These are the individual factors of the denominator, and then we need to determine a and b. So this is done in exactly the same way as we did before. We'd need to multiply by this denominator, and then eventually solve a linear system, and we would find a few cups of coffee later, we would find that a is minus 3, b is 4. And once we know this, we can determine the inverse Laplace transform. Here's another example. We have 3 terms, s plus 1, s plus 2, s plus 3. All right, then this means we need to break down the rational function into 3 terms, a over s plus 1, b over s plus 2, c over s plus 3, and so on and so forth. If you like, you can do this as an exercise. So this was case 1, where we have in the denominator real poles of multiplicity 1. We have simple real poles. What happens if we have real poles again, but one of them happens to be, or more than one of them happen to be multiple? Like in this case, we have s plus 1, s plus 3 squared. Then the only difference is that for the pole with multiplicity 2, we need 2 terms. If we had a pole of multiplicity 3, we would need 3 terms, and so on. And the decomposition is as follows. You see this s plus 1, we treat this as we did before, a over s plus 1. But for s plus 3, we have these 2 terms. We have b1 over s plus 3 plus b2 over s plus 3 squared. So we don't just write b over s plus 3 squared, we include also this term. We have 2 terms. So now we need to determine a, b1 and b2. We multiply by the denominator, as we did before. So these cancel out, these cancel out, s plus 3 and the square cancel out, s plus 3 squared and s plus 3 squared cancel out. We write it again here neatly. We need to expand this s plus 3 squared, and we need to do some multiplications here. And after we do all this, after a little bit of tedious algebra, we end up with this equation. And this is an equation, an equality of polynomials. On the right hand side, we have a degree 2 polynomial. We have a quadratic polynomial, something times s squared and so on. And on the left hand side, we have a constant. And this means, if we have a constant, means practically it's like we have 0s squared plus 0s plus 1. So this means that a plus b1 is 0. And this coefficient, 6a plus 4b1 plus b2, is also 0. So this is equal to this. And the constant term is equal to 1. So we work as we worked before. We formulate a linear system, the unknowns being a, b1, and b2, and we determine the values of a, b1, and b2. Then we plug in the values into the partial fractions expansion, and we have this term, which is easy. We know the inverse Laplace transform of this. We have this term, which is the same as before, and we have this term, which is a little more strange because we have this square in the denominator. So this begs the question, what is the inverse Laplace transform of such a term? And we have these formulas here. As we said before, the apologies, I have a typo. The inverse Laplace of 1 over s plus a is e to the minus at. The inverse Laplace of 1 over s plus a squared now is t. You have time t multiplies here the exponential t times e to the minus at. And in general, you have this formula with which you can see what happens if you have a third power in the denominator and so on and so forth. So now we need to use this. So the inverse Laplace transform of my function f is 1/4 times e to the minus t. The second term gives minus 1/4 e to the minus 3t. So you see this 3 becomes the exponent here. This plus 3 becomes minus 3. Or to put it differently, observe that this term has the pole minus 3. And this pole is exactly this number here. So it's worth keeping in mind that whenever you have negative poles, like here we have minus 3, you end up with a term that goes down to 0. And this will be very important when we talk about stability. Here again in the first term, you have a pole minus 1. And again, it's negative, so you end up with a term that goes down to 0. And the third term, you have s plus 3 squared, so you have again minus 3 in the exponent, but you have times t. Well, okay, this is again a term that goes down to 0. It behaves like this. And then it drops exponentially. Right, so that was the case where you have multiple poles. You can have also a pole of multiplicity 3, like here. Guess what? Here you need to decompose into 3 terms. So you have something, this asterisk means something, whatever, it doesn't really matter. You decompose into a over s plus 1, and then this becomes s plus 2 squared, s plus 2 cube, with 3 different coefficients to be determined. Also, you could have s plus 1, s plus 2, s plus 3 squared, s plus 4, let's say to the power 4. Let's see what happens. Then s plus 1 gives you this term, s plus 2 gives you this single one term. S plus 3 squared gives rise to 2 terms, let's call them c1 over s plus 3, c2 over s plus 3 squared, and I think you got it. This term gives you 4 terms. And then in this case, you need to determine 1, 2, 3, 4, 5, 6, 7, 8 coefficients. Right, so that was case number 2. Let's move on to case number 3, where you have pairs of complex conjugate poles. And these look like this. You can have a function that is something, whatever, over s plus 1, let's say, and then you have a term of the form s plus 3 squared plus 10 squared. So this means that we have the pair of complex poles, complex conjugate poles, minus 3, because of this, plus minus 10j, the imaginary unit. And we can factorize it, of course, following case 1. We can say, if we like, that this is s plus 1, and since this is really 2 poles, we can write s plus 3 minus 10j, s plus 3 plus 10j, s minus 1 pole, s minus the other pole. And then we can expand like this. This is a perfectly legitimate approach. It comes at the expense of having to deal with complex numbers, and in general, it is a little more tedious than the method I'm about to show you here. I believe the method I'm about to show you comes with a little less algebra, which is good. So the alternative method is, instead of doing this, to decompose like this. You have b1s plus b2 now in the numerator, and in the denominator you keep exactly the given term, s plus 3 squared plus 10 squared. And of course we need to know how to determine the inverse Laplace transform of this quantity. And here comes proposition 5.4 from the textbook that gives you this formula for the inverse Laplace transform of generally b1s plus b2 over s plus a squared plus b squared. Let me write a little note here that in this general case, the poles of this term are minus a plus minus b j. And we see that the result is some number k times e to the minus at, a being this number here, times a sine of bt, so the frequency here is b, this number, plus phi naught. So this tells us two things actually here, two key observations, is that this number a determines whether this exponential goes to 0 or whether this exponential goes to infinity. So if this a is positive, this means that this goes to 0. In other words, if your pole with a positive is on the left-hand side of the imaginary plane, then you go to 0. And then this is number A. What about B? B determines the frequency. So the higher your B, the more oscillatory, so to speak, the higher the frequency of your output. And these numbers K and phi naught are determined by these formulas. Okay, you can look them up whenever you have to. You don't need to memorize them. Just note that in the formula for phi naught, you have the two-argument inverse tangent function. Let's give an example. Take f of s being some numerator over s plus 1 times what you see here, s plus 2 squared plus 5 squared. This means that the poles of this function are minus 1 from the first term and minus 2 plus minus 5j from the second term. We can say a few things about the inverse Laplace transform of this even before we carry out all the algebra and end up with the formula for the inverse Laplace transform. We can tell that whatever it is, certainly we have a decreasing exponential because of this minus 1, and we have some term that is oscillatory. It has a frequency of 5 and it goes down like the exponential of minus 2, which is beautiful because we actually if we're interested just in the form, in how the output looks like, how the inverse Laplace transform looks like, this means we don't really need to determine the exact formula. But nevertheless, let's do it. So we have a over s plus 1 from the term s plus 1. And for this part, we have what we said before, b1s plus b2 over this this term that has a pair of complex conjugate roots. So we'll multiply by the denominator and we end up with this equation over here. And you can expand s plus 2 squared and you can do all these multiplications so that the right hand side of this equation becomes clearly written as a polynomial of the form coefficient times s squared and so on and so forth. So I've done this for you, and we have a plus b1 s squared plus this term times s plus this term being the constant term. And on the left hand side we have s squared plus 1, which I've written down as 1s squared plus 0s plus 1. And now this is an equality of polynomials. Polynomial equals polynomial, which means once again that the corresponding coefficients are equal to one another. So this is equal to this, because there are the coefficients of s squared, the coefficients of s are equal to one another, and so on and so forth. So we can write down a linear system with unknowns a, b1, and b2. We can solve the linear system and we can determine a, b1, and b2, and we have these values. We have carried out our partial fractions expansion, and we have that f of s is this plus this. Now you see we have these fractions in the second term being the slightly more interesting term. Okay, the inverse Laplace transform of the first term is just 1 over 13 times e to the minus t, alright? Now the second term has these unknowing 1 over 13. I will take this 1 over 13 out just for convenience. And now I just need to determine the inverse Laplace transform of this term, which looks slightly better. And I can take the inverse Laplace transform, and from the proposition you see here, we know that this is equal to k times e to the minus 2t times sine of 5t. 5 is this 5. And this minus 2 is this 2. Plus phi naught. So now using these two formulas, I just plugged in inside the given constants. For example, you see here you have b squared, and then this b shows up here and shows up here and so on. This b in our case is this 5. b equals 5 in our case. Or you see this s plus a squared, a is equal to 2 in this case. So using these formulas, we can determine that k is 12.1062 and phi naught is 1.7033. And overall, we have this inverse Laplace transform. So that was case number 3, and that's all you need to know. There is one case we didn't cover, which is the case of having complex conjugate poles like these here, but you may have a square or you may have a cube there. Then the formulas become a little more lengthy, so I think let's just skip this case, but you can find details in the textbook. Now, to summarize everything and see how we can apply these things when it comes to solving initial value problems, let's have a look at this figure once again. You start with your ODE, you apply the Laplace transform, you end up with an algebraic equation, and then you take the inverse Laplace and you have your solution. So let's see this in action. Here's an example. Take this differential equation, x double dot plus 0.1 x dot plus x is equal to 1. And I'm giving you also some initial conditions. You'll need them. X at 0 is 1, x dot at 0 is minus 2. So using the properties of the Laplace transform, in particular, we know that the Laplace transform of x dot is equal to s times Laplace of x minus x at 0 plus, and we have a similar formula for the Laplace of x double dot. We discussed these properties in the last video. You apply the Laplace transform and you end up with this equation in the S domain, which is an algebraic equation. And you can now solve for x, which is your unknown, and x, this is a big X of S. And this, in a way, as we discussed last time, is your solution, but in the S domain. Now we need to go back and see the solution in the time domain. So the first thing we need to do here is to factorize the denominator, because you have s squared plus 0.1 s plus 1. You know that this has two roots, but you don't know if they are real or complex conjugate. So let's factorize. You take the discriminant and so on and so forth, and you end up with this. So the poles are apparently minus 0.05 plus minus 0.9987 J. I don't know how this happened. Then you can do a partial fractions expansion, and you can decompose this as A over S, because you have an S over here. It corresponds to a real pole at 0. And then you have B1S plus B2 over this. And this is because here we have complex conjugate poles. Then you would have to determine A, B1, and B2. And after you do this, you can take your inverse Laplace transform using proposition 5.4, the one I showed you before, and you have your solution, which looks like this. But even before you reach this final result over here, even by inspecting x of s, you can tell that you have 1 over s, you have a pole at 0. So this means that you have an inverse Laplace transform which is equal to a constant. You have a dc component in your x of t. And you have e to the minus 0.05 t, and you have a sine of 0.9987 with this frequency, sine of 0.9987 t. And indeed, this is how your x of t looks like. So these steps are just for you to be able to determine this number and this number, and, well, this number. Right. So thank you for watching, and I'll see you next time.